Does the universe curve back on itself? Are there habitable planets at Alpha Centauri? Is anyone working on orbital refueling? All this and more in this week's question show. It's time for the question show. Your questions, my answers. As always, wherever you are across my channel, if a question pops in your brain, just go into the comments down below any video, write down your question. I'll gather a bunch of them up and I will answer them here. Now, we record this show live every Monday at 5 p.m. Pacific time. So if you want to come and hang out during the live show, ask follow-on questions, chat with other people in the comments, go ahead and do that. All right, let's get into the questions. Garmin 1966. Please talk about the idea that the very early universe was the size and shape of, say, an orange or a grapefruit before it exploded to infinite size, which it obviously wasn't because everything we know in our universe says that it's flat and infinite. I've talked about this before many times, but I feel like this is the hill that I will die on, that I will, if I help illuminate one part of science in the world, it'll be this thing, because I used to be confused about it. And there's an episode where I talked to Dr. Paul Sutter and he explains it to me and slowly and carefully, and I finally get the concept into my brain. But you hear this all the time, that the press says that the universe was once the size of a grapefruit and then it expanded with the Big Bang. And that is wrong. It's like so wrong on so many levels. And once you get it, then hopefully this will just, like, all of this misunderstanding will just fade away. So today, when we look out in all directions, we're seeing the light that has been traveling for 13.8 billion years. And the actual size of that universe is like 92 billion light years across, because we've been moving, the universe has been expanding, the galaxy's been moving, and sort of the total distance, so the place where the light left, has been traveling for 46 billion light years, even though it's only been traveling for 13.8 billion years of time. That is the observable universe. It is this sphere around you that you can observe if you have, like, if you just strap cosmic microwave background radiation detectors to your eyes and you look in all directions. That sounds great. I think I want a telescope like that. If you look in all directions, you are seeing the edge of the observable universe. And the one that you see is different from the one that I see. And the one that someone sees in Alpha Centauri is a different observable universe. We all see a different observable universe. And the universe is getting less dense over time, and this observable universe is getting less dense over time. And so if you go all the way back to the beginning, then yeah, the observable universe was once the size of a grapefruit or a volleyball or a whatever it was, right? And so then if, like, teeny tiny little you standing in the middle of this teeny tiny little observable universe, you would see this sphere around you, and that would be all the universe that you could see, because it had taken a nanosecond for the light to get to you from that point. But just outside your observable universe was more universe. An infinite amount of universe, maybe, or if it is a finite amount of universe, it's a very big universe. Like, the actual universe is at least 1,000 times larger in volume than the universe that we are able to see. And the answer is that we don't know. Like, it could be finite, it could be infinite. Astronomers just don't know which one it is. The universe is so flat that when they try to measure the curvature to figure out the size of the universe, they can't measure it. It is practically infinite. And we may never know if it's finite or infinite. And so, people always wonder, they have this sort of stuck in their brain, like, how did it go from this finite grapefruit-sized thing and then kaboom to this infinite universe going off in all directions? And so the point is like you caught the mistake in communication, which was that it was either infinite before, and yet you just had this observable universe, and then it just went off in all directions, or it was finite before, but still bigger than the observable universe, and that everything that we're seeing is just this observable universe all the time. And so it was infinite before the Big Bang began to decrease the density of itself, and it's still infinite today. Or it was, finite, but so big you couldn't even calculate it, and it's still finite, but now even bigger today. I'm sure you've noticed the planet name above my shoulder here, and this is a way for you to vote for what you thought was the best question, or the best answer, or the best question-answer combo, whatever tickled your fancy, vote for that. And so last week, the winner was Bob, who asked, how can something come from nothing? And you like the question? I mean, like, we've all had that question, right? Like where did this whole universe come from? And I hope you like the answer. So thank you everyone for voting. If you are interested, so just watch to the end of this video. You'll see these Star Wars planet names appear above my shoulder, and then watch to the end, and then just put into the comments down below the name of the planet that you thought was the best question this week, best answer this week, and we will count them up and we will celebrate that next week. Keith Carnage 9516. Is the CMB slowly changing? I feel like it should also be fading, but it might not be noticeable. So this is the other big question that I get, and hopefully I will sort of make this one stick as well. And I apologize for those of you who've heard this answered many times, which is that when we look out to the cosmic microwave background, we are seeing it the moment it was first released into the universe. So it's not like you're seeing like a very old part of the universe and then you're seeing other parts of the universe around it. You're seeing this moment in time. And then a second later, a minute later, you're seeing a place that's a little bit farther away experiencing that first, 300,000, 380,000 years after the Big Bang. And then an hour later, you're seeing a region that's just a little bit farther experience that first moment 380,000 years after the Big Bang, when the light is finally able to release. And so the CMB is fading, but it's only fading because the place where the light was released to us is farther away. And so the photons are just a tiny bit more stretched out into the microwave, pushing towards the radio spectrum. And so in the far, far future, millions, billions of years in the future, the wavelengths of the cosmic microwave background, they'll still be there. They're still photons. It's just that they will be more redshifted farther and farther into the radio end of the spectrum. So it's not like it's getting dimmer, although it is getting dimmer. It's getting, because the light is sort of expanding in all directions, and so it's getting harder and harder for us to be able to see it. But it's not like the CMB itself is fading away. It's just as bright as it always was at each point in the universe when this light could finally escape out into space. Now, I know it's a headache, I know it's a head scratcher, but that's how it works. Ray Oshima. On the edge of the universe, does space curve back on itself? So at the beginning of this video, I talked about this idea of an infinite universe, but I was sort of oscillating back and forth saying like the universe is infinite, or maybe the universe is finite, but it's really big. And as I said, according to astronomers, like the minimum size of the universe is like 1,000 times larger across than the universe that we can perceive, but it could be infinite. But if you do have a finite universe, like what would that be like? And if there was, like, if you could somehow see right out to the edge of the finite universe and not have to experience this time, then what would it look like? And so it would kind of be like if you were standing on the Earth and you looked in one direction and your vision could go curving, following the curvature of the Earth all the way around the Earth. And if you look far enough, you would see your own back. And then if you looked to your right, you would see the left side of your body. If you looked to the left, you would see the right side of your body. If you looked down, you would see your feet. But anyway, so if the universe is finite, then theoretically it would wrap. And so if you traveled in one direction for a long enough period of time, you would return to your starting point. All this time, of course, the universe would be expanding and you would be having to travel farther and farther. And of course, there's no way you could travel as far in a human lifetime, but it doesn't matter, right? And so in any direction you want to go, yeah, it would wrap on itself. It'd be like a game of asteroids, but in 3 dimensions. Or it's infinite, and then you just never return to your starting point. Ralph Chang, what are the chances that there is a habitable planet or moon in the Alpha Centauri system, including Proxima? So the Proxima Centauri one is the easier question to answer, of course, because Proxima Centauri has we know a planet in the habitable zone around it. Now, Proxima Centauri is a red dwarf star. The planet is probably very close. We know that Proxima Centauri has flares. The planet is probably tidally locked, but in theory, there could be liquid water on the surface of this planet orbiting around Proxima Centauri, which is incredibly exciting. Like the closest star that we have to the sun just happens to have a planet in the habitable zone. Obviously, more data is required. Like, hopefully this is the kind of thing that the James Webb Space Telescope can look at, or maybe some future extremely large telescope, something like that, is going to be able to observe it. But the Alpha Centauri system is a whole other situation. You've got two stars that are kind of like the sun, roughly the same size, mass as the sun, orbiting around one another, orbiting far enough that you could have planets in orbit around one or the other star. And we don't know if there are planets. Astronomers at one point thought they had detected a planet, but then it turned out to be an error, and that's been canceled out. But there is a really interesting mission that's being developed called Ptolemy. And what this is going to do is watch the two stars simultaneously. And because you're going to have these two stars in the field of view, the two stars will act like a brightness standard candle for the observations of the other stars. So it will be watching the two stars and watching how they change in brightness compared to each other. And watching them far enough, it will eventually get to a point where it'll be able to sort of sense whether one or the other star is changing in brightness because it's got planets orbiting around it. And it should be able to detect like this radial velocity. So the star could go moving a little bit towards us, a little bit away from us, on some regular pace. And the Ptolemy mission is actually very inexpensive, probably a CubeSat sized mission, and should be launched in the next couple of years. And actually, I've got an interview with the principal investigator of the mission. So what are the chances? I mean, we don't know, but it sure is worth searching and worth dedicating an entire space telescope just for this job. Sandy Batches, whatever happened to SOFIA that was in a modified 747? Can it be repurposed? SOFIA is like the best idea. Like, I really love this idea that you've got this 747 airplane, and then you cut this big chunk out of the side of it and you mount a sizable infrared telescope. Then they fly it at an altitude that's high enough that it through most of the Earth's atmosphere at a place like the Earth's atmosphere is blocking certain wavelengths of infrared light. But if you can get above this, it kind of is acting like the James Webb Space Telescope. But then you can land the airplane, you can refit the telescope, you can upgrade, change new gear. And SOFIA was amazing, has contributed a lot of incredible discoveries. Like, we learned a lot about the water on the moon. We've learned a lot about galaxies, about stars, newly forming planetary systems. SOFIA's been a workhorse, but it was old. And you've got the James Webb Space Telescope, which is sort of more powerful and works in the same wavelengths as SOFIA in every way. And so once you get to this point that now with a few lines of computer code, you can just turn this telescope and make some observations, as opposed to fueling a 747 and flying it and it not being as powerful as JWST. So that budget gets allocated onto other projects. But I think the underlying idea of testing out your technology on an airplane is really solid, because you can iterate. And when you think about how much time and money was spent building JWST, yeah, it's a phenomenal instrument, but it costs $10 billion and it took 20 years. And so you can rapidly iterate your technology and your ideas. And there's actually a long history of not necessarily airplane-based telescopes, but balloon-based telescopes for sure. There are a lot of balloon-based observatories flying all the time with different instruments. And in many cases, they are testing out these instruments at high altitude, and then they find their way into space telescopes later on. So I think there is this really valuable series of test beds. You've got sounding rockets, you've got balloons, and you've got things like SOFIA, a way to test out different ideas, make sure they work before you put it into space telescope form and fly it off in a place where you can't work with it anymore. And of course, I've got an interview with the director of SOFIA here on the channel as well. So if you want to learn more about the telescope, although we did the interview before the mission was canceled. So, and she knew, but she couldn't tell me, I'm sure. So anyway, you can definitely check that out. Mr. Orb. People keep talking about magnetic pole reversal. Is that a real thing? Yeah, it's a real thing. The north and south poles of planet Earth will swap on a occasional basis. It takes about 700,000 years for it to happen, although we are overdue for a magnetic field reversal. Like, it doesn't happen regularly on a schedule. And we actually see something very similar with the sun. The sun has an 11-year cycle where the north and south poles will switch, and you go through this period of solar minimum where you don't see a lot of sunspots on the surface of the sun, not a lot of flares, not a lot of activity. And you move towards solar maximum, where the magnetic fields on the sun are most turbulent and sort of quite like widening where they're coming and going from the sun, and then the poles flip, and then you move towards solar minimum again, and then back. And it happens, the entire cycle takes 22 years to go through. We're actually approaching solar maximum right now, which is why we're getting a lot more sunspots, a lot more auroras. It's a pretty cool time to be watching the skies. And so this thing happens with the Earth. Now, scientists aren't really sure why the poles flip on the Earth. I mean, it has something to do with the planet-wide magnetosphere that, we know that the Earth, the spinning core, causes this dynamo, and at some point you get this flip. It's not like the core itself flips over, but just the polarity of the planet flips over. And it's happened many, many times in the past. Like I said, it happens every few 100,000 years, and we don't see any mass extinction events that are correlated with the times that these polar alignments have happened. And it's really cool, actually, how geologists figured out that the poles flip is that they can measure the direction of iron particles that are in the lava as it's flowing out, and then they line up with the magnetic field of the Earth before they cool and lock in place. And so they can find these old lava fields, and they can see how they go from one direction to another direction over time, allowing them to measure when these pole flips happen. So yes, the Earth's poles do flip. We're overdue for a new flippening, and it doesn't seem to cause that much damage, if any, when it actually happens. Yes, that Kareem. It looks like both SpaceX and Blue Origin are relying on the ability to refuel a spacecraft in microgravity. Has refueling of vehicles in space been done before? Maybe at a small scale, but not on the large scale. So this idea of refueling a spacecraft in space is one of the keys for both the SpaceX Starship and the Blue Origin lander, Blue Moon, to be able to get to the moon. And so the plan for, say, SpaceX Starship is they're going to fly a Starship up to space. They're going to then fly more tankers. They're going to transfer fuel to Starship, and then it's going to be able to fly off to its next destination. And Starship is fueled with methane, which isn't that difficult to fuel to work with in space. The plan for Blue Origin is they're going to be using liquid oxygen and liquid hydrogen, and they have to be stored cryogenically. They have to be stored cold. And hydrogen is a really tricky fuel to store for any long period of time. It's the smallest atom. It wants to get out of anything that you do. And so nobody, like, maybe there have been some tests that I'm unaware of. Like, I know on board the International Space Station, there was a recent experiment that would try to do refueling on the station, and they had like a little refueling nozzle that they extended, but nobody's done this like at scale, and it's going to be necessary. Now, there were plans. United Launch Alliance put together this whole plan for a space-based refueling system a couple of years ago, and developed new technology for it, and tried to make the pitch that instead of building really gigantic launch vehicles like the Space Launch System, that you launch with more traditional, established, well-known rockets, and then you just refuel things in space. And so you can imagine there would be this space infrastructure of refueling systems located around the Earth-Moon system, or maybe at various Lagrange points. And I really like the idea. Like, that's sort of why I'm going into such detail on this, is that I really like the idea of refueling in space, but it is currently a big unknown. There are a lot of engineering technical challenges to do this, and we need to see some tests. And it feels to me like this is, like, when you look at Starship and you say, like, the orbital reentry is going to be the big issue. How is that thing going to get back from space? Is this going to work? Are those heat tiles going to stay on? But as big of an unknown is going to be refueling in space. And one of the things when SpaceX took on the human landing system for the moon was there was a big technology transfer from NASA. So a lot of their orbital refueling development, science work, research that had been developed so far was transferred over to SpaceX for them to build from, for them to build the human landing system, and then obviously to use that technology for them to be able to go on to the moon and Mars or whatever they want to do. So put a pin in it. It's a big unknown. We don't know if this is going to work yet. We don't know how it's going to work. It's going to be more complicated than anybody thinks, and we'll have to watch and see what happens as it all gets worked out. If you like my answers to your questions, as well as the other things that we do at Universe Today, consider joining our Patreon club. This allows us to keep minimum ads for everybody. Like, as you can see, there are no ads during the video. As a patron, you also get an ad-free experience on universetoday.com for life. Even if you unsubscribe, you'll get ad-free videos, early access to interviews, as well as other perks that are exclusive to our Patreon community. Thanks to everyone who has already subscribed, and welcome to the recent newcomers: Angelo Bartolos, Tim Mitchell, Edward Atwell, Joanne McDonnell, Jeremy Boards, BT Atkin, Mona Evans, Grant Hasty, Edward Kramer, Tony Lano, Charles Walker, and Ryan Birdie. Join the club at patreon.com/universetoday. Just Gudrian. Say two stars orbit each other. Could an orbiting planet swap stars during its orbit? Get captured by one star when they're maybe close to each other and then make a figure 8-shaped orbit? No. We know that there are planets orbiting around multi-star systems. So the one possibility is that you've got two stars that are very close to each other, and then the planets are orbiting very far away from those two stars. And so the stars act like a single mass at the center, and then you got the planets going around it. And so when you think about it, like, if you were standing on one of those planets and looking, you would see the two stars always very close together in the sky, kind of like how we see the sun and Venus are always relatively close together in the sky. And then the other possibility is that the stars are very far apart. They're so far apart that they don't interfere with the orbits of the planets that are orbiting around them. And then in that situation, you've got two stars are orbiting one another, right, with a common center of gravity. And then you've got each one of those star systems has planets around it, like the Alpha Centauri that we talked about earlier. Although you could have both. I mean, you could have, in sort of like the perfect situation, you could have two stars that are orbiting around each other. You've got a planetary system, but the stars are orbiting far enough that they both have planetary systems. And then around that, you've got planets that are orbiting around both stars. But it would be very tricky to kind of get the perfect situation. But no, you're not going to get the situation where planets are going to be transferred from one to the other. What you're going to get is planets kicked out of one star system or the other, or they're going to be crashed into other planets, or they're going to be absorbed by stars. So it's just not a stable arrangement that will last for any long period of time. And this is actually sort of one of the ideas in the three-body problem, that the Trisolarans come from this star system with two bright stars and one dim star, and they started out with 10 planets and they end up with one planet because of all the mayhem caused. But I'll let you read the book or watch the TV show. It's on YouTube right now. Arav Bathla. Can we use gravitational waves to understand about the matter which it travels through, planet stars? I asked this a few weeks and saw some cool news. So theoretically, yes. So when a gravitational wave passes through an object, like it passes through a planet or it passes through you or it passes through a galaxy cluster, it will be affected by the object. It'll be affected by the gravity of the object. And you can sort of do this thought experiment that we can detect gravitational waves because we are siphoning a teeny tiny little bit of energy away from the gravitational wave as it passes through us. Like conservation of energy, right? Like if we aren't reducing the energy in the gravitational wave, then we can't detect it. By detecting it, we are slowing it down a tiny little bit, or like we're a rock in this ripple that's passing by. And so I guess the question you're asking is like, could you look at the frequency of the gravitational waves that are reaching you and then see, oh, these gravitational waves have been changed. They were caused by a black hole, but now they've gone through a galaxy cluster, or they went through a watermelon, or whatever. So theoretically, maybe, but practically speaking, it sounds really tricky, and you would wonder. But I mean, we are just at the beginnings of the field of gravitational wave astronomy, and we are only detecting the most enormous events in the universe, like the collisions of black holes. But as the next generation of observatories come online, you've got the space-based observatories like LISA, better ground-based observatories. There's plans in the works to do like a 40-kilometer long-armed version of LIGO, like much more powerful. We could get to the point where we're starting to see, you can imagine things like we're detecting primordial gravitational waves from the Big Bang that passed through swarms of primordial black holes. And you might see a signal in that. So never say never. Driving in Luton, does the ISS need to be refueled on occasion? Yeah, absolutely. When the various spacecraft dock with the International Space Station, like the Progress cargo ships or Crew Dragon or the Uncrewed Dragon or the Dream Chaser, the Cygnus spacecraft, although there won't be any more of those for a while. Anyway, they are often transferring propellant to the International Space Station. So it has thrusters on board and it has propellant tanks, and it uses those to boost its altitude from time to time so that it won't re-enter the Earth's atmosphere. It can also do these boosts with some of the attached spacecraft, but yeah, it has propellant on board and thrusters. The Arcanes, could there be life on a planet whose inhabitants can never leave because the escape velocity is too high? Yes. Sounds so sad, doesn't it? That you could have life born on this planet and the force of gravity is so strong that no solution to the rocket equation will work out, and they're trapped on the planet. But the gravity would actually have to be pretty high. Earth's gravity makes it feasible to launch rockets into space. And when you think about rockets are big. I mean, they are skyscrapers, but payloads are large. Like you can launch 10 tons to low Earth orbit. There's more, maybe eventually like 100 tons to low Earth orbit. Like there's some pretty big rockets out there. And if you lived on a place with double Earth gravity, you could still launch an equivalent of a Saturn V rocket. It's just that the final payload would be 100 kilograms, but it would still work, and you would have 10 stages, but it would still theoretically work. And life could absolutely exist on a world with double Earth gravity, but that would be a pretty special world. Even if you had a world that was twice the size of the Earth, twice the mass of the Earth, you would still not be experiencing twice the gravity on the Earth just because of density. In fact, it would be closer to Earth. Anyway, but if they could figure out some kind of denser energy source, maybe they could figure out how to build solid hydrogen, metallic hydrogen, like what's found at the core of Jupiter, or maybe they could master antimatter propulsion systems, then everything changes for them again, and maybe they could go to space. And you don't need to launch tons. You just need to be able to bootstrap your way up into space. And so if they could launch, maybe they get really advanced in their robotics and their self-replicating robot systems, and they build this spacecraft that's just small enough to get to space and start building more copies of itself, von Neumann probes, and they build this giant space infrastructure, and they bring down tether hooks and provide a ladder that they can allow more and more of them to be able to get up into space. So I think it would be a pretty special situation to completely get cut off from space itself. But yeah, can you imagine, I'm sure this is a science fiction story somewhere, that you arrive at this world and the world has heavy gravity, and you talk to the aliens and they say, give us a lift, we'd like to come to space. And you're like, it's too dangerous. We can't land and then return to space. So you're stuck. And like, would you like to join our Galactic Federation, but nobody will ever come and land on your planet and you can never leave? That's hard. Anelio de Meglio. Can what happens inside very dense neutron stars be extended to black holes? So are you talking about this idea that very large neutron stars, very massive neutron stars can have strange matter in their interiors? This was a news story that we picked up this week at Universe Today. When you've got enough mass in a small enough area, then protons and electrons are mashed together and you get neutrons. And that's what a neutron star is. Like, there's so much gravity, so much density that you can't even have protons and electrons anymore. You just get neutrons. But that if it's like right at the edge of becoming a black hole, well, then in fact, you're at the core of this neutron star, you're smashing even the neutrons so that they're kind of squishing out into quarks, which are the fundamental building blocks of neutrons. And so you've got this soup of quarks inside this neutron star, and then wherever it's like not quite as dense, then you've got neutrons surrounding that. And you add a little more mass and the whole thing just pushes over the limit and goes into the form of a black hole. And so like, we don't know what is inside the event horizon of a black hole. The gravity is so extreme that no signals can get outside of it. And so one possibility is that, yeah, a black hole is just like whatever comes after strange matter, like the density. You get to a point where maybe the quarks are crushed down into their fundamental object and the escape velocity exceeds the speed of light, and you get this object with this extreme escape velocity. Or maybe the thing just keeps collapsing down and becomes a singularity. And over time, and maybe it's increasing at an accelerating rate. It's getting smaller and smaller and denser forever at an accelerating pace. And so, we can't know what's inside the event horizon. So, astronomers practically, mathematically speaking, consider that it is a singularity, but we can just never know what's inside the event horizon. So maybe it's a thing, or maybe it's an infinitely small thing. Whatever it is, it's a lot of mass compacted into a very dense area. Yanis, can the asteroid belt, give it enough time, produce a new planet in our solar system? No, the asteroid belt can never produce another planet in the solar system. A couple of reasons. One, there's not enough material. Like, I know the asteroid belt feels like there's a lot of stuff there, but the main asteroid belt actually only contains about 5% of the mass of Earth's moon. And so if you just like collected all of the mass in the asteroid belt together, it wouldn't even hold a candle to the moon. And that is not a planet. I mean, it could theoretically be a planet if it's orbiting around the sun because it's in hydrostatic equilibrium, but it'd have to clear its orbit. Anyway, no. And then the other thing is that the very existence of the asteroid belt is due to Jupiter. And I know a lot of people tell you Jupiter is your friend. Jupiter is trying to protect you from asteroid impacts. That's not entirely true. Jupiter is sort of influencing the asteroids in the asteroid belt and shoving them inward. And so all of the near-Earth asteroids that we have coming past our planet are because of gravitational interactions with Jupiter. It's constantly pushing them inward. And so Jupiter won't let the asteroid belt coalesce into one object. It keeps jiggling them and pushing them around with its gravity. Steve Ross, could a simulated universe one day be so advanced that we could accurately simulate and depict events from the beginning of the universe all the way to me making breakfast toast this morning? So there are some really advanced computer simulations out there right now of the universe where cosmologists are simulating all the various factors that come from the Big Bang, all of the mass collected in different ways, and then watch how it unfolds over time. And they mix and match different amounts of dark matter, dark energy, stars, baryonic matter, black holes, and see how the universe progresses over time. And these require supercomputers. Like, some of the biggest computers in the world are used for this process, but they are enormous, like in terms of the size of the simulation, because you've got a lot of particles. You are simulating a galaxy, and the galaxy has a whole bunch of stars in it, and you are trying to simulate the movement over time of the gas and the dust and the stars and the black hole and how they interact with each other and all of the gravitational forces. And the more particles that you add, the more precise your simulation is going to be. In fact, like when you think about predicting the weather, like weather prediction has gotten pretty good. I don't know about you, but like I find I can usually mostly trust my weather forecast now, and that's because of supercomputers that now Scientists can predict all of the different ways that the wind is moving, the sun is heating, the different ocean currents, and they have these giant computers that help them make these climate models short-term and long-term over time. So, like, how good will those simulations be is just a matter of how good our computers are going to become in the future. You know, could you ever get to the point where you could simulate you making toast? Maybe. The ability for a computer to simulate reality is always going to be less than the actual reality itself. You know, like the computer that would take to simulate reality would require all of the energy and resources in reality. And so you would just be simulating reality and you wouldn't actually be in reality. So that would be really tricky. But the simulations are getting better and better. And it's pretty exciting to see how powerful and how accurate these simulations have become. I've been reading a lot of books. Thanks to everybody for suggesting books at the book club. This is, of course, a list on Goodreads where you put in books. I pick them at random or whatever interests me, and then I read them, and I tell you what I thought. That is the book club. So the most recent one is The Ministry for the Future by Kim Stanley Robinson. And if you haven't read any Kim Stanley Robinson books, you really should. And the most famous one are the red, blue, green Mars series, which talks about humanity first arriving on Mars, building up cities, eventually terraforming Mars, and sort of all of the shenanigans and hijinks that ensue. And they are foundational. Like, if you're into human space exploration, those books they should be on your shelf and you should definitely read them. And so the book that I read recently was The Ministry for the Future. And this is Kim Stanley Robinson's future book. And the concept is really neat. Like, we know that there will be like 100 billion human beings have lived so far, and there are going to be untold hundreds of billions, maybe even trillions of human beings in the future. And yet we are taking actions during our current day that has an impact on them for the future. And so what this book theorizes, like, what if the United Nations got together and set up the Ministry for the Future, essentially a group that could provide a vote for the unborn, for the future generations of humanity. And of course, what would happen is that everyone would ignore them and everyone wouldn't care. And so how would they be able to acquire the resources? How would they be able to convince people to take these things seriously? And it's like this, like, what I love about the book is that, like, in times it's very dark and talks about very awful things happening, but it's also very hopeful and comes up with a lot of really practical ideas. And so the characters are fairly thin, but the ideas are so good, and hearing them played out over time and hearing these ideas worked and those ideas didn't work. And it's quite inspiring, and sort of see this vision of the future where things are getting more under control and things feel more sustainable for the long term. So The Ministry for the Future by Kim Stanley Robinson. So keep those book suggestions coming. Right now I'm reading the third book in the Culture series, which is terrific, but keep them coming. All right, those are all the questions that we had this week. Thank you, everyone, for asking your questions in the YouTube comments. Thanks to everyone who showed up live to the show. Remember, we do this every Monday at 5 p.m. Pacific time. And don't forget to vote. If you want to stay on top of all the important space news, join my weekly email newsletter. I send it out every Friday to more than 60,000 people. I write every word, there are no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast, or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent and keeps ads at a bare minimum. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Just Paul Davis, Vlad Shiplin, Jay Dennis, David Giltinan, Modso, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verabioff, Andrew Gross, and Josh Schultz, who support us at the Master of the Universe level. All your support means the universe to us.